Thank you all for coming. As you know, this is the third of our lectures, of 4 lectures that are all part of this this show that Fatos Ustek has curated, and today we're going to be talking about patterns in science and within art. As an artist, not a scientist, my intent often is to destabilize and create more questions than answers. As we have discussed previously, a scientific model will usually answer questions, but a successful artwork should perhaps raise more questions than it answers. In this vein, my hope for today is that for many people in the room who've entered thinking that they understand what patterns are, may leave with a different, altered concept of how ubiquitous, intrinsic, and fundamental they are. They are not just superficial visual entities, but invisible systemic forces that seem to pervade through every aspect of the world. It is deep within our human nature to search for patterns, the design contained within a system, sometimes when they are never there. Now we're going to go straight into the questions. So Liliane will be first. I mean, Liliane has spent much of her career working on a particular form, and this is quite in keeping with many ways that artists work. So you have Monet return to the same lily pads in the same pond at the same time of day every day and endlessly search the permutations, the colors, the reflection of the light across the surface. Solowitt used the cube and endlessly explored the permutations of that. Carl Andre, the brick, and created endless geometric arrangements of those forms. I have spent 30 years working with the tetrahedron, which has been an endlessly rich vein for me, both philosophically and geometrically and conceptually. And you can see many of those pieces within the show. This one is called Offcut. But Liliane similarly has worked tirelessly exploring one particular geometry, which I think she'll explain now.
In 1959, when I started working as an artist, basically studying, but studying by myself, I was drawing, and I drew a circle, and inside the circle I drew a triangle. The circle was full of strange creatures. The triangle was absolutely empty. And I thought about it, and I thought, well, the circle really relates to my inner emotions, and the triangles to my mind. And I wanted to be that triangle and not that circle. Now, I found that the relationship between the circle and the triangle are very, very interesting. And I think for years I've been playing with that relationship or that pattern between the way the circle can transform into the triangle into the circle. There is, for example, now I work with cones, but circles can become cylinders, can't they, in 3-dimensional balls, and cones and spirals. So the cones, this particular cone that you're seeing there, which is a video, we'll show the video, right, is made out of fiberglass. It's about 2.5 meters high. It's white, and it's dissected by planes of perspex. The perspex are inlaid, having taken out the material that they were inside the cone. So we lay these layers or planes of perspex, if you like, in elliptical, sort of tilted positions. And what happens is very interesting. When the cone spins, I made the video really short, but my talk is a little bit longer. When the cone spins, there is a relationship, or you could say a pattern set up between the different lines that are moving. In fact, the lines are not moving at all. It's the cone that's spinning, and you're seeing different parts of the cone in motion. And when you see it fluidly in motion, it dissolves itself, which is why I called it zero gravity cone. this was probably about 72, I started making these aluminum and bronze solid cones that when you touch them, I mean, they were meant to be manipulated, when you touch them, transformed into organic shapes. And what interested me was this capacity for a formal geometric shape to become an organic, living, moving, living shape. And I thought that was another interesting, if you like, pattern.
And I think there's something similar to the tetrahedron. There's something so simple about the cone, and yet so unbelievably complex. That there's so many things that lie underneath the surface. That these elliptical planes, these cuts through it. Well, I mean, this sort of keeps giving in terms of those sorts of amazing impacts and those amazing kind of implications.
Well,
and
cones
properties.
are ubiquitous. They're the cones in your eyes that see color. They're the traffic cones on the street. They're stupas. They're steeples. They're skirts. They're totally everywhere. You see cones. In fact, I was told that that the solar wind drops into the polar, into the north, into the poles through a conical form. I don't know quite why it was conical, but it's conical, and they call it the lost cone.
Wow.
And that creates the aurora borealis, or so some scientists think. It's disputed. This work that I've chosen to show you was made. I think that I wrote down when I made it. 1980, I think 82, right. And it's called split spiral spin. It's in plan. It's a spiral made out of 8 arms, 8 parabolic curves, and it's made from perforated steel. It's 40 foot high.
And you can enter into this, can't you? It's an immersive experience. You walk through the Moray effect.
When you see it, for example, people in cars would stop and think they were looking at a glass, structure. But in fact, when the sun hits it, if you look at the other slide, where's the other side?
This, go back one. This one.
It's opaque. Mm-hmm. So you have an opaque and a transparent structure. The interference patterns are for me, very interesting. I heard David Bohm talk about his theories. I mean, this was at Birkbeck, and there were about eight physicists there and me. And I had been invited to go there, and he spoke about reality as an interference system. And that fascinated me, and that was why I made this sculpture. We can go to the next one. So this sculpture, which I made quite recently in 2019, is a conical skirt. It's 6 meters diameter and made out of cloth, and at its edge, there's a strip of LEDs that goes right the way around the edge, the diameter, the circumference of the skirt. We spin the skirt, but it's not simple. The spinning is not at one speed. You cannot accelerate it in a linear fashion. It's a very, it took a long time. Yes, you can show the video, actually.
So this is a still, that's a still of it, and then the video is here.
Yeah.
Is that?
So there you see it beginning to spin, so it's quite irregular, and then it starts, the faster it goes, the smoother its pattern, and you can see the waves. There are actually 3 waves, and there are always 3. And from above, if you look at it from above, there are 3 spiral arms. They're not actually waves; they're spiral arms that whirl around with this piece which I call Gravity's Dance.
And have you woven in? Is it hyperbolic? So you've woven in more pieces than would lie flat. Is it more that
I've made the first ones I made, which I called spinning dolls. I had 4, one on top of each other.
Wow.
And I also made it with crocheted material. So what was so interesting was that a crocheted material full of holes was actually much easier to raise, to levitate, than a solid material. And when using a solid material, it had to be heavy. It was extremely difficult to figure out the way the material reacted and try to get
fantastic.
It
seems to never repeat, and it's very chaotic. It's wonderful.
It's quite chaotic.
But when you lay it flat, is it a circular piece of cloth?
It's a completely circular cloth.
You haven't added one more slice to make it hyperbolic.
No.
Because it appears here like it's like a sea cucumber, that it's become.
Yes.
You've added one more slice of pizza.
That's its movement. That's its movement. But
it's amazing. It's because it's sort of
circular skirt, basically. And in fact, my idea was the idea of a skirt, of a feminine skirt that becomes this almost diabolical movement, you know. So in this particular piece, it becomes quite dark.
Yeah, it's like a whirling dervish.
Whereas the earlier pieces, the whirling dervishes are actually very light, very luminous, and they're people. There's no person here, but I hadn't thought of the whirling dervishes. I had just spun the material, and when I had so much difficulty, and somebody said, "Oh, the whirling dervishes," I had seen them years ago, and I thought, well, what do they have that I don't have? And I realized they have hips. That was the key. When I understood the hips, then I understood that I had to have a flat, circular base, sort of to start with, clamped down, with the cloth clamped down on it, and from that, it would rise.
Right.
Otherwise, it went into a vortex.
Okay.
You see?
Okay.
So that's the curious thing about this very curious piece, which I showed actually at EGO in Pisa, which is the European Gravitational Observatory.
So a key example of finding the solution in nature.
So this piece is more recent again. And it'll be up in November again at Louis Cubitt Square. It was commissioned as a kind of Christmas tree. I hate to say that, but it was. And I made this, which I don't think looks like a Christmas tree, but anyway. It does light up at night. And basically the reference to patterns is because I take one. Well, let me explain it from the base. I divide the circle into 20 equal units, and then I put opposite the central. If you take it sort of centrally, I put a very tall pole, right, which is here 12 meters high, and then the next 2 poles in increments. I shorten the poles on either side, always the same, and they are attached to the central pole, and then the next ones are attached to the ones before, and each pair are attached. So basically, they're supporting each other. So it's, if you like, it's almost a self-supporting structure.
Yeah.
And the interesting thing is that the 20th pole, because there are 19 poles, the 20th pole just had there was no place for it, so it had to be left open.
It's beautiful. So it's a progression.
So it is a progression that creates this kind of arch, this kind of wing.
Yeah.
Well, I've worked a lot with progressions, actually. But here you see it at night. It's colored day and night, and in the left-hand photograph,
this one.
you can actually see the colors during the day. And then at night, you see them again. And the black points are where the actual poles interfere. So again, interfere with each other. So you get this. And then there was one more.
And then there's this. Well, I was going to.
Oh, you were going to. Yeah.
Well, I've been doing a residency in Nottingham University studying the early universe and black holes and black hole ring down, black hole mergers, and looking at LiDAR detectors and gravitational waves. It's been really exciting. But this diagram came up time and time again. These sort of very conical representations of the origin of the sort of initial conditions leading through the rapid expansion to the present day. But there is this almost universal sort of representation of this journey as a sort of cone. And so it really, I sort of love. Whenever I look at your works, I really see sort of see this sort of idea of that sort of expansion or duration represented through that thing. And I think one of the great things about being in this wonderful context and with most likely all of these budding and amazing mathematicians is that these sort of augmented minds seeing work in a new way, you can interpret them in such fresh ways. And I've had so many endless interpretations of the work through the lens of mathematics here that I never would have thought of. But it's so valid in itself. But these conical representations of space and time, your work for me, in my sort of interpretation of them, which is just one interpretation, that was such a sort of important thing with those. And I have one of your beautiful resin pieces on my windowsill in my bedroom, which I really love. But it's also an example of how pattern isn't just superficial. It's not just scrimshaw, but pattern sometimes pervades through things. It's everywhere. It's not just a visual, two-dimensional, superficial thing. It's intrinsic. And with those resin ones, it's really lovely because it's opaque and translucent, but you see the colors through every strata of the layer. So you've got this. It permeates through. It's not just a decoration. It's essential and fundamental.
Thank you.
And then
I don't know whether you can see the drawing, which looks like
the drawing's the next slide. So it's a bit confusing because we've got two slides there the same.
Oh, I see.
And then this is telling you what's next.
Well, perhaps the drawing came first, so maybe you'd show the drawing.
Yeah.
Okay. Is it visible? Yeah. So in the late 70s, I wanted to get back into drawing, which I hadn't done for a while, making these cones, actually the first cones that I made. And I started just by making little lines. And as I made these lines, I realized that they formed a pattern. Now, what I was trying to do was just to use one specific shaped line, so a mark, if you like, not a line, a mark. And that mark repeated, just by changing its angle, would completely change the way the drawing came out. And so a pattern or a structure was actually created from this relationship between marks. Now, if you see the sculpture that I made much later, in the late 80s, 88, that was made for the government chemist, and who told me it was similar to DNA. So basically, again, it's perforated steel, triangular V-shaped triangular forms, empty triangles, if you like. And each one is just shifted in very small increments, sort of up. It's hard to explain. And that shift is the only thing that differentiates them. Otherwise, they're exactly the same. And then this shift in their spatial arrangement creates this corkscrew spiral that's held floor and wall.
Beautiful. Where is this piece now?
This piece now is in storage. What happened was the government decided to sell the government chemist to the American company.
Okay.
And the American company decided to move. So my piece was given back to me, which was very kind of them, instead of destroying it. Or,
I share I have deep sympathy and share your problem.
Yeah.
So now we're going to move on to Marcus, but I just, before we do, I thought this would be a nice segue. This is a piece called Loop System Quintet, which is a piece I made back in 2007, and it's a series of 5 machines which take a very specific ratio. There's a 9-to-8, a 5-to-4, 3-to-2, 3, and then a 4-to-5. So there's different harmonic ratios, and I use these as a springboard. And like with the reason I put this on with you, when you sent me your slides, I saw that beautiful toroidal, like with the spinning dervish work, if I may call it that. And I was there was something very similar to this, where there is this kind of chaotic but yet predictable kind of loop. And there's this sort of dichotomy with this, because when you see these bulbs and these lurching around, there's a sort of violent movement to this. But actually, when you take a photograph, there's something quite different. You suddenly see these sort of steady, eternal, floating forms which are never changing. And these pieces create these beautiful sort of floating toroidal knots, which again have this maybe that spline, the elegance that you had on that light, which is sort of this beautiful toroidal curve. And this is a sort of version. It's called it's kind of poor man's version of Time Splice, where I spent a very long evening, about 12 hours, making a 10-second loop, where I filmed a piece, moved the camera, did a 30-second exposure, moved the camera 1 degree on a track, took another 30-second exposure, and took it again. And by the end of the evening, I was pretty kind of dazed by watching this thing spinning around. But I did it, but it creates this beautiful sort of eternal kind of loop rotation. But I felt there was something really, there's a sort of spirit there that I hope is similar, in that there's a spirit of investigation that is like a scientist. But actually there's a similar result of this beautiful floating kind of glorious thing but it came to me as a surprise. It was a real eureka moment. So I felt like a scientist with this. It was like, oh my God, I've discovered something. But in fact, I hadn't discovered anything or invented. I came across something that already existed. That whole dilemma of invention and discovery. But these pieces have led on, these harmonic pieces have led on finally, and it's really good timing. But I've got this piece in Liverpool Street that's opening tomorrow, which is called Manifold. And it's essentially a toroidal knot at the top that falls downwards. Time is moving downwards, and it's essentially a picture of a chord falling into silence. And so, and it's made of bronze. It was made in Spain a few years ago, and it's been in storage for years. But they finally finished the station, and so it's quite a timely thing. But this is the culmination of those early researches with spinning a light bulb really fast, and then taking a photograph of it, leading to these sort of mathematical kind of these mathematical works. So Marcus, we're on to you, and I've been really, really, really enjoying reading your book again, and so flattered to be mentioned in it. I also, and all your hero Gauss has been really sort of on my mind a lot, and these kinds of really the way everyone can interpret numbers in a different way. I mean, it's quite exciting to me, this sort of idea that everyone in this room can think of a number but see a different thing within it, and that to me is something that I think maybe you can explain with your with these next slides.
Yeah, well, it was this word pattern that's kind of intrigued me about our conversation, because I think pattern for an artist immediately conjures up something visual, maybe 2-dimensional, a pattern on your clothing, on the wall. And for me, it has a very different resonance. And actually, it's key to how I often define what I think a mathematician is, because I think people who are not part of the mathematical world find what we do a little bit mysterious. Physicists, so they bang atoms together in a large collider. Chemists blow things up. Biologists collect butterflies. And I'm sorry, I shouldn't. But what is it a mathematician? What are we doing all day in our offices here? And I think a lot of people think we're doing kind of long division to a lot of decimal places or something. But actually, I try to define a mathematician as a pattern searcher. And I think that's what is the essence of being a mathematician. And very often we're looking at the kind of chaotic world around us. We're getting information, data from there, and we're trying to see, is there any logic to this? Is there any algorithm, any pattern, rule that helps us to navigate what's going on? So I thought I would try and introduce you to the idea of patterns from a mathematician's point of view by giving you some numbers to look at and challenging you to see whether you can find the pattern. So I'm a big believer that mathematics isn't a spectator sport. So it's very important that you engage your mind. So I've got a few challenges for you here to get your brains into my mode of pattern thinking. So the first sequence, can you spot a pattern which will tell you what the next number is in the sequence? 1, 3, 6, 10, 15, 21, 28. Anyone shout out what the next number? 36, exactly. And how did you get 36, sir? Yeah, how did you get, what's the pattern there? It is quite easy. I thought I would start you off nice and comfortably. All right. This one, you're just adding the numbers up one at a time. And in fact, Gauss, very famous story of Gauss, who was able to spot a pattern which helped him to tell the 100th number on this sequence without having to add up all the numbers up to 100. And one of the shortcuts I talk about in my book. But maybe we'll click on to the next slide, because it tells us these are called the triangular numbers, because there's a very visual way to think about it. If we click on to the next, perhaps if you shoot over, I'll is it? Okay. Because we can view these very visually. It's the number of stones you need to build up these triangles. And actually a triangle can help you to find a formula, because if you put two triangles together, you get a rectangle, and counting things in a rectangle is easy. It's base times the width, the height times the base. And so a formula would be half that number. So we actually understand these numbers very well. They are very simple numbers. The next sequence is one, if you've read the Da Vinci Code, you might have met this one. This is a very famous sequence. So what's the next number in this sequence? 1, 1, 2, 3, 5, 8, 13, 21. 34, exactly. And you got that by adding the two previous numbers together. So there's the pattern here. You build the next number out of the previous numbers. You probably know a name for these. Fibonacci numbers, yes, exactly. But actually they shouldn't be called the Fibonacci numbers, because Fibonacci was not the first to discover these. He discovered them in the context of nature. So in the natural world, we find these numbers coming up all over the place, because nature also builds things by taking what we have seen before and building on that. So they have a natural sense of growth, which is why if you take a flower and count the number of petals in that flower, invariably it's a number in the Fibonacci sequence. And if it isn't, that's because a petal's fallen off your flower, which is how we get round exceptions. But actually, these were discovered not by mathematicians and Fibonacci, but by musicians and poets in India, who realized that there was a pattern to the way rhythm built up if you use long and short beats. And they wanted an algorithm to somehow generate all of these complex rhythms of the tabla. And they found that the Fibonacci numbers were the sequence that told them how they built. So they should be called the Hamachandra numbers, actually. But okay, the next sequence. 1, 2, 4, 8, 16.
32.
32 seems the most obvious answer, but actually 31 is the next number in this sequence.
Yeah.
You go, what? Right, but 32 is, it looks like it's doubling, but this is very important. You need to know where your numbers are coming from. So in this case, these numbers are actually describing something called the circle division numbers. And this is, if you take a circle and you put a point on that circle, you just have one region. But if I put 2 points, I can join those up and I get two regions. If I add another point, join all the points up, I have a little triangle and 3 regions around the outside, 4. So you think, oh, right, this is easy. Every time I add a point, it somehow doubles the regions. And you explore a little bit further, you add 4 points, you get this nice little envelope and 4 regions around the outside, 8. So you think, oh, I'm making a conjecture. This is clearly doubling. Something about this, every time I put a point and join them up, probably everything gets divided or something. And again, the 16 is the next one. But then a surprise happens, because when you have 6 points, you'd only squeeze a maximum of 31 regions out of this. So for me, this is important, because mathematics would be very boring if everything was so predictable as just doubling. And for me, the joy of mathematics are these sudden turns in direction, where a pattern you think is building up can suddenly go in a different direction. And so we have a formula for this, but it's slightly more complicated than just doubling. So you have to take the number of points, and it's a quartic polynomial, but we've understood the pattern, and with that pattern we can make predictions. And I think that's important, because patterns are important to us as a species, because they are our best tool for looking into the future. Because if we understand a pattern, we can make a prediction about where we're going next. How do we know about climate change? Because we've looked at the data, and the data seems very clear about what we are facing ahead of us. What about your diagrams of cones, you see? How do we know that we've come from a singularity? It's because if we take the data back, it collapses down to this singularity. And Roger Penrose's last session was talking about we can know what's going to happen in the future. And as he said, it's a very boring future where we just kind of just dissipate and just all become light. Okay, so you're all getting very good at this. So I've got
Is that the future?
The future is very boring, according to Roger. Yeah,
We become light?
yes, which I actually think isn't too bad.
I wrote a book.
Well, you're obviously you
That
spot the pattern, and there we are. We've got the future. That's that. Everything is going to decay into just pure energy, gravitons and electrons. A little more challenging sequence for you. So you're very good at spotting these patterns. What about the pattern in this one? 2, 9, 10, 11, 13, 16.
Coming.
It's coming. Okay, right. You've all gone very quiet, and I know there's some professors of mathematics in the room here, so you've probably been holding back and saying, "Oh, well, those are jolly easy. I will wait until the really difficult ones." So, no, it's people shaking their heads, which is good actually, because these are in fact the lottery ticket number winnings for 28th of September. Not yesterday actually, but yes. Oh my gosh, no, it's the 28th today of September. This is last year, I think, but yeah. Else, perhaps go and buy a lottery ticket before the newsagent closes. But this is another important message. We saw that patterns can go in an interestingly new direction, but sometimes things don't have patterns, and that's a challenge, that we so want patterns that we try and look for them everywhere. And but that said, even random things quite often, we've Fermat and Pascal produced the theory of probability to be able to tell things about even randoms. Okay, my last sequence is probably one that you know about. It's the prime numbers. These are the most important numbers in the whole of our subject, and these are numbers that we've been trying to look for a pattern to understand how they're laid out in the universe of numbers. We've been trying for 2,000 years, and we still really don't understand how to predict where they're going to be. There are infinitely many of these scattered through the infinity of numbers. They get rarer and rarer. They never run out. But we're beginning to feel there's our greatest unsolved problem, one that people are working on here in the department, is called the Riemann hypothesis, which is actually an articulation of the fact that these may not have an obvious pattern to them. And that's actually quite difficult to prove something doesn't have a pattern.
Yeah.
So that's a little bit of what, for me, what the word pattern is about, understanding an underlying logic to something.
Fantastic. It's really fascinating. And I very serendipitously had dinner with someone last night, and I was telling them about this talk, and he gave me this amazing word that I had never heard of before, and everyone I've talked to subsequently hasn't heard of it before, but it's so key to this lecture, and it's so there is this sort of innate yearning of mankind to sort of find the design or the pattern behind something, and that relates to a sort of a creationist instinct, or a sort of this idea that and we spent hundreds of years with Copernicus to try and find the pattern or the Platonic makeup or the architecture of the solar system, and yet then we finally realized that it was a series of catastrophic events and everything was quite arbitrary. But then we're still now with the universe sort of trying to take that further and find the secret of everything for that. But there's this wonderful word that it's called apophenia, and it's a condition, and it means seeing patterns in things when there is no pattern. And but it's a really interesting, in regard to this lecture, it's really interesting in terms of those lottery tickets or with the prime numbers, that in fact the final result of all this might be that there is no pattern. and that the universe is potentially messy, or it isn't this sort of, like the schism in the hallway when you come in. The schism, no matter how many times you put those 80 triangles together that form the 20 tetrahedrons, it will never quite reconcile. And you can try all you might, but there will never actually be the complete coherence where there is this sort of this grand design of everything, and everything may be, like the solar system, quite messy and coincidental.
Yeah.
It's just a speculation.
No, it's
but
interesting because, I have a box upstairs which is just full of letters from people with patterns that they think they've discovered in huge, differently varying areas, and very often they feel like numerology. And scientists are generally very down on numerology because that's generally associated with the kind of the desire to find patterns where there aren't. But actually, I'm less down on the numerologists because I think at its heart is the spirit of what we do. We're open to the idea that maybe something bizarre is happening here. And so if you take Kepler, for example, Kepler came up with this mad idea that the way the planets were arranged in our solar system had something to do with the way the platonic solids could be put inside each other. And it looked brilliant. It sort of perfectly explained why there were the number of planets we could see, the distances between the solids was right. And he even built this. I mean, you've probably seen this thing. It's lovely. It's absolutely...
It's beautiful. It's very compelling. It's very attractive.
It's a beautiful thing that he made with all of the platonic solids, one inside another. And then, of course, we discover several more planets, and the platonic solids have run out. We've only got 5, and the whole thing is blown out of the water. But I think that spirit of just trying to look for an explanation, a pattern to explain how the planets were, of course, that's actually the same spirit that led to him understanding the laws that control the way the planets move, Kepler's laws. So
don't we follow patterns unconsciously? In any case, our brain is constantly, even though we're not consciously looking for a pattern, we have to function, and our functioning is through this, if you like, automatic visualization of patterns without actually seeing them.
Yeah, I think
you know what I mean?
Yeah, absolutely.
I mean, for example, I one day going out to dinner years ago, I remember having a little bit too much to drink, and then driving across Hyde Park Corner when there were no traffic lights. I just remember sort of driving across and thinking, my God, how am I doing this? I mean, cars coming in every direction, and yet we do it very easily, There's
the other cars may have had a different view. But I think it's, when people say, oh, I'm not a mathematician, actually I think the brain has evolved to be mathematical at heart, that this element of looking for patterns is how we've survived. Those that didn't spot the pattern were unable to look into the future and act accordingly. And actually there's a kind of big argument about consciousness and the fact that a lot of the illusions that happen to the brain are because we have to fill in so much, and that is about filling in due to the patterns we've seen in the past. And if something breaks that pattern, then it has to reassess itself in relationship to the outside. I mean, so I do think that it's how we have to operate. And you talked about time quite a lot with Carlos and Roger last time in this session, and I think again, if you think about time, Roger was talking about the fact that photons do not have a concept of time, but how do we have a concept of time? I think that's highly related to the idea of a pattern, because something needs to repeat itself in order to be able to understand a kind of unit of something that you're going to compare everything else against.
Also, young children have no concept of time. It takes quite a long time before a child actually understands time.
Because they've got to build up that recognition of something repeating.
5, 6 years, maybe 7 years sometimes.
Absolutely.
I mean, there's evidence that the caves in Lascaux are actually a calendar where the dots that you see on the wall, I mean, there are wonderful pictures of animals and things, but the dots on the wall are actually about repetition of when the stags are rutting or when they're mating, and this is, and you've got the Pleiades right at the beginning of this sequence, and it's saying, look, these are repetitions in the calendar, and therefore this is how we can have a concept of time.
And speaking of time, Fatos, you've did this very intense project, I think, which I'd lead in with that, which is, I mean, you're going to talk more about invisible patterns, but you did an incredible show that was 50 exhibitions in 50 weeks. So very much about indexing in pressured time situation.
I mean, like, to be honest with you, so many things to respond to. And it's also very nice to be on the speaker seat today. So I think I was very obsessed with time, and I was very much obsessed with the kind of like being in the, now. And that obsession led me to do like a trilogy of exhibitions. I even ran an art magazine that was called Now is Where, but that meant it's not like now is, where. It was actually, so whenever you say now, it is singular, but whenever you mark that now with some associative experiences, then it becomes a plural past. So all of our writers, of course, misspelled it, but it was, like more of a conceptual exploration of like what is happening. But I think for me, what's been very interesting is like studying mathematics, and I mean, what you say is really true. It's also about like kind of recognizing patterns, but also at the same time, it's kind of like the euphoria of finding one, And I think I'll first talk to you about this project, which is like an unprecedented artistic research that I did 11 years ago. I used to teach at Linköping University in Sweden, and they have this department called Vision Forum, which was like a really open department, and I led this couple of projects that were artistic research projects, but they were open-ended. We didn't need to kind of like come up with an exhibition or any outcome, and also at the same time we could just do whatever we wanted. So with a curator colleague, Anna Gretz, we actually started infra. And infra, it means like ultra thin. So if you know Marcel Duchamp, he's like the kind of, let's say, one of the, I don't like godfather, but like kind of like a really, important fathers or thinkers of contemporary art. So Marcel Duchamp came up with the concept of inframonths. And inframonths is like the dust that collects in your shirt pockets or the warm seat when you get on a bus. And it's really this kind of, let's say, ultra thin layer that is kind of like connecting different realities. So as you are seeing here, we kind of like wanted to treat ourselves. So we invited 6 artists with Anna. And you could go to the next slide. We wanted to treat ourselves like empty vessels. So we sat in a, economics class on like matchmaking theory at the Cambridge University. We sat in astrophysics class at the Imperial College. But then we also had a training with, this Gurdjieff practitioner. Gurdjieff made this anagram, and he actually says that, there's 9 patterns in humans' lives, so that. And when we are born with those patterns, it's basically what we are constantly evolving around. It's very esoteric, but also there's like special movements in your body that you could do to kind of like overcome what is limiting you. And then we also even, played Go and many things. So I have quite a fun 1-minute video, which was made by one of the artists who was participating in the infra. Yeah, maybe we just watch this.
We were invited to take part in a project called Infra, INFRA. The plan was to sit in on established formats for knowledge distribution and activities. Everything would be connected. Otherwise, the details of the process of the coming year was a complete mystery.
Yeah, so it was like a 1-year research project where, we were trying to find what connects different formations of knowledge production. But the artist was really responding on to the fact that we started with, finding out the Masonic imprints in London, and then it was really, stretching the content as much as possible from the spiritual to the kind of like hardcore scientific. There's another project that, was really, so I've been mostly working with, let's say, different temporalities of curating. And this project really won me the badge of crazy. It glows in the dark. I have it on my left shoulder. It's imprinted. So I curated 50 exhibitions in 50 weeks with, you know, like 11-hour turnover from one shelf to another. And there was like the kind of cue, but we could perhaps go to the next slide with the GIF. So just wait. Yeah, perfect. So it's showing. So it was at the RCA in 2015. I had this one room, but at certain times of the year, I could also use the ICA theater. And then also I even commissioned artworks at Beste Village, which is just around the corner from here, and literally received 60 million visitors before COVID, second best visited place in the UK. And so this Fig 2 was basically a brief to me. And this happened 15 years ago. I mean, like in the beginning of now, 23 years ago. At the year 2000, Fig 1 was curated by Mark Francis, and that became like an epic show in the sense that it really kind of like created the buzz that the London art scene needed, you know, before the pop-up show term was coined. And also at the same time, it was really giving a platform to young contemporary artists, because most of the gallery scene was still looking into impressionist paintings and, you know, other kind of like classical modern art forms. So with Fig 2, it was really about like thinking, you know, how could I create a platform for artists to be, you know, like as experimental as possible, and really create a non-institutional platform for them to take risks. And I have kind of like a map of my curatorial methodology, so we could perhaps go there, because I can talk about Fig 2 for 5 hours or 5 days, depending how much time you have. Because it was quite an epic project. We had like 50 exhibitions and 148 collateral events. Yeah. So Fig 1 was one exhibition, one artwork at a time that was taken out from a studio, brought into the Georgian townhouse that it was using. For me, in 2015, just doing the replication of Fig 1 was too boring. So I thought, okay, I have 50 dots, as you see on this beautiful paper. So I was interested in that, how can I kind of like, we can go to the next slide, how can I kind of like create a continuity? So I thought I could actually have an overarching theme that connects all the exhibitions. And then I could perhaps like have a linear connection of like, you know, what the previous exhibition did, the next exhibition could kind of like in a way respond to it, expand it, or take it, you know, like what you were saying, like sometimes making a sharp U-turn. I mean, first of all, I was so ambitious that I thought all my family and friends would come all my 50 shows. They didn't, but there were some 20 people that they did. We kind of had a loyalty card that we would stamp their loyalty card every week, you know, because when I moved to the UK, I was, you know, so perplexed about loyalty cards. And, you know, probably for the first 5 years, I lost a lot of money and free coffees just because I never collected one. So I thought, okay, we will have a loyalty card, and they got a free publication. But so I thought, okay, I'm going to connect all the exhibitions. And what Fig 1 did was like they started with Richard Hamilton, a kind of like a in-progress work, and bookended Fig 1 with the completed painting by Richard Hamilton. I thought, brilliant idea. So I will start with an artist, but I will start with someone who's young and who never had a solo exhibition in London before. And I will kind of like show an in-progress work with them and an end the exhibition with it. But then I thought, fine, but that's not enough. I studied topology. I was very much interested in topology while I was an undergrad student. So for me, linearity is interesting, but then it's predictable. So then I thought, okay, if we could go to the next slide, how could we do it? Then I thought, okay, maybe it would be great if I could have like these kind of, let's say, vague groupings. You know, I started with what is in a line, and that line in the first one was like made into carpets. The second one actually was by Charles Avery, so it was into drawings, but also he is very much interested in non-Euclidean spaces. The third one, it was actually a representation of memory. The fourth one became a prose and poem, etc. And then I thought, okay, I could then have like areas where I kind of like have a focus on fashion or performance or different things. So it was like I started doing these kind of groupings. If we go to the next slide, and I thought that was not enough. So, you know, if you've played like snakes and ladders, you know, like sometimes you throw the dice and you go to number 42, but then you fall into 17. So I thought, okay, not everyone is going to see the whole 50 show offer, which was very important to see, but they wouldn't, then how could I still create a sense of an ethos of a project where if you came only to, you know, like week 2, week 47 and week 28 and still had an idea of what week 2 was about. So then I started kind of like creating connections that were almost like across, you know, like non-linear collections between weeks. So it would be either like, let's say, if the third week artist was talking about, let's say, film and then memory, then I would bring another person at the week 37. But that was still not enough. So if we go to the next slide, then I thought, okay, I need to punctuate something so that there is still this kind of like confluence of like artistic practices coming into one another. And sometimes I would also invite, you know, like scientists to collaborate with artists, or sometimes it would be cybernetic experts or, you know, like people from all these different areas. But I thought I need cluster points so that there's almost like these kind of like gravitational areas where people feel like, okay, there's something more about it. That was my curatorial seminar program, which actually Lauren came to almost all of them. So it was eight projects, that was like 8 lectures that was all about looking at curatorial practice. And then we did workshops and we did different things. So if you go to the next one. So this was actually my curatorial methodology for the 50 exhibitions. And I mean, we also have a diagrammic representation of it, but I thought, you know, this might be good to showcase my patterns of thinking.
Why did you choose 50?
I didn't.
Somebody else chose 50.
50 chose me, yeah.
50 chose you.
It's so interesting to hear you talk about this afterwards, because I saw these slides and then I was seeing these 50 dots, and I love these. They're like they're like a wonderful 1950s drawing of a sort of amino acid or something. There's something very logical about it, but there's something also a bit crazy about it, which I love. But it's got this wonderful sort of. But there is this. I mean, if I was a doctor specialising in apophenia, and I laid out all these dots and asked people to draw the thing, I would say you have a bad case of apophenia with this.
It reminds me a little bit of Georges Perec's Life User's Manual, because you know the idea that he has an
obstruction.
An apartment block with 100, so it's a 10 by 10 apartment block, and he puts these rules on which he wants. He makes a Latin Greco square out of it, so that and each room has to have one thing from this thing, one thing, and it just that constraint leads him to incredible kind of creativity. And then the way you go around is dictated by a knight's move, and then there's one room missing, and I think those kind of constraints are what's really exciting.
Yeah.
You put a pattern. Force a pattern on, it can take you somewhere really interesting creatively.
Yeah, absolutely. I mean, like Georges Perec is really an influence because he was part of this Oulipo movement. It's a, Oulipo, French literature movement, and it's like oeuvre, literature potentielle. So it's like the potential literature, the oeuvre of potential literature, if we could, bluntly translate. But, like Georges Perec, they would all put themselves obstructions, and then those obstructions would be the ground for their,
and they used to have a lot of mathematicians come along, and it was really what are your constraints? Are they useful for me as a writer? I think that's what's so exciting about that.
Yeah, there was also a crossover because, for instance, Georges Perec had a MIT residency, so he actually was invited to write a novel based on binary code. It's called like How to Ask for a Raise from your head of department, if that should be the case.
Oh, maybe I should be reading that.
Oh, it's such a good one. It's hilarious. It's really good. It's really written in a binary code. But he also wrote this novel in French without using the letter E, which is the most frequently used letter in French. And then there's a fantastic translation to English, which is used. The whole book is written without the letter A.
Wow, I mean, these things, as artists, as designers, sometimes these constraints are very liberating. It's the liberty of constraint, which is sometimes design needs constraints in order to sort of sometimes progress. So I was going to now show you this object as a sort of end of the lecture. This piece has emerged from 20 years of trying to develop interference patterns and sort of disrupt surfaces like you with these moire patterns and optics, and letting the sun transform surface as a form of camouflage, as a form of, and I have this piece called this is called The Patterns of Absence, and this is all about interfering holes. There's hundreds of thousands of holes, and these two discs are rotating very slowly as they think. If you leave the lights on for a second while I set it up. So this box is called the Library of Absence, and it's designed by, it's sort of inspired by a 1950s dance set that my dad gave me when I was a teenager, and it still works. It's got wonderful valve technology in it, and this piece is, and I've kind of had it, and I still have it in my house and play these 45s on it, and so I've got this kind of this skin which is quite similar, reminiscent to that, and the whole thing is a briefcase. So you can sort of carry it around. It's anodized aluminium, and then you open the box up, and and then it reveals a contraption inside, and then here we have got the elastic. We've got 64 interference patterns. So these are all unique patterns that I've kind of collected over the last sort of 20 years. They're all different things, and they're sort of color coded. But essentially, it's you've got a light and a rotation. So it counter rotates. So it essentially achieves what you're seeing up there. But we've got these endless different permutations. You can put like for like, which with the moire, the kind of golden rule with moire is that the patterns have to be the same for them to create the holographic effect. If you change the scale of the pattern, the effect is destroyed. You can orientate, you can place them further apart, you can change the pitch, but they have to be the same for them to interfere with each other. So it's quite fractal in that way, is that if you don't feed the same thing back into itself, it doesn't work. Daryl, you could turn the lights off now. Need to put the slide on a black slide. I'll just do that. Okay. So these are, so you can slow it down, and I can move this back so we can get a better sense. So you have these different, the speed is also is a key thing, so you can slow it right down. Essentially it's a sort of library of all these sort of different perforations. So if I then try a different one, you can then, the thing that becomes unpredictable is you can mix discs together, which then creates a very beautiful kind of interference. Some of the interesting ones, are the simplest ones in repetition, are actually the most interesting. And again, that in mathematics, I think there's a mathematician called Wolfram who sort of deals with these ideas of interference and complexity. And apparently, his argument is that the simpler the patterns in repetition, the more quickly you arrive at complexity. So there's a sort of, the more complex the patterns are, the longer it takes for you to reach. So these are just simple slits. Which it's very surprising how much sort of flux and how much change happens within these patterns, and it sort of moves in different directions, which again is sort of very surprising. And this is the one that I regarded as probably the least interesting before I tried it, but yet it has almost the most complexity of all of them because it's the simplest. So I think we can. I'm happy to show you all these things after the talk, and for you to have a go with them if you want. But maybe we can turn the lights back on.
The interference is much stronger there than
I can. But the other thing is that you can play with these colored discs, and you change the colors, and you can mix them together. So this becomes an optic thing in itself, and you get the dilution of reds and greens and blues through the disc. So you get the same kind of interference you would get on the disc piece, the wall-based piece. This is a piece it's produced by a Swiss bookmaker called Edition 5, which this is the sort of first time we're sort of showing it. It's going to have a book in here and the discs in there, and it's essentially a sort of she's produced it as a sort of a limited edition. But it's the sort of most sophisticated design we've done in the studio in terms of a kind of actual sort of mechanism that is sort of boxed mechanism. Great. Okay. You go into this? Yeah. So I thought I think we're running out of time, and I think they need the room at 7. But before we open the floor to questions, I just thought I would sort of end on this kind of nice sort of this nice font of the number 7. But I think in terms of everything that we've talked about tonight, there's a sort of interesting kind of conclusion that we can sort of discuss briefly about this sort of, I guess, like an artwork, that you have this amazing potential to interpret an artwork, and the more successful an artwork is, the more people in a room can interpret it in different ways based on their experiences, their gender, their education, their loves and traumas. We've talked about this in previous lectures. But again, I think numbers, again, have the same potential. Like with Gauss in the classroom, no one else could see the things that he saw, and he's found what you would regard as a shortcut to solve this thing. But he looks at the numbers, and some people may see a duration of time in this number. You would see a prime number. So this could be the 7-day week. Someone may say this is partitioned into a 4 and a 3. Some people may see it in a more numerological way as some sort of projected meaning of heaven. But I mean, I don't know what we can open it to the floor. And what does 7 mean to different people? I mean, it's free to be as philosophical or as religious or as mathematical as you like. But I think that the point is, I think that these things, they aren't. There's the other wonderful thing that I suppose in terms of a pattern, and that reminds me. I've got a final question for you, Marcus. That there is sort of that numbers are they're not just quantity. And someone who I have spent a long time sort of researching and making work inspired by her is Ada Lovelace. And so she was this incredible visionary who is widely regarded as the first programmer, but mainly because she was the first person who saw that numbers could be more than just quantity. They could be entity. They could represent things that wasn't just apples and pears, but they could represent data, or they could represent information. And so she's the first person, decades, if not century before in other people, who saw they had this amazing mind shift to see that potential of number. And then the last question I wanted to ask you all is the sort of, if I may, is this idea of a pattern that may have changed your life or changed your practice. Then Marcus, I think you had an interesting.
Well, my area of research is trying to understand symmetry and what symmetrical objects are possible, not just in our three-dimensional universe, but in higher dimensions as well. And so I suppose, if one thinks of just a two-dimensional wall, what symmetries are possible, and the Alhambra is a great place to explore those patterns. So in a way, I'm trying to understand just what might be possible in, high-dimensional Alhambra palaces and things. And our first thought was that everything looked very chaotic, and the way you put symmetries together, it just seemed to be a complete mess. There didn't seem to be any order to it. And I suppose for me, one of the exciting moments, as you said, those moments of discovery are those seeing new things is what we live for. Those aha moments. And for me, it was actually understanding that there was a pattern, almost a Fibonacci-like rule for how many of these things you'll see. And but I think the most exciting thing was constructing a symmetrical object that had a pattern hidden inside it that nobody had expected before. That the conjectures were telling us they were going to do one thing, and but as I built this thing, suddenly there was like a pattern emerging from a completely different area of mathematics, something called elliptic curves. And suddenly seeing this like pattern inside this object has completely changed the direction of my research. It's opened up a completely new tunnel between these two, and that pattern emerging, just seeing something appearing in a completely different area, for me, constructing that object was kind of my greatest aha moment. If I was going to get a tattoo, that would be what But it actually is interesting because I can't draw them. It's not something you can see. It's something you can only describe in the language that we use to build symmetries. So it would be a sort of linguistic expression of this kind of pattern that I sort of that I'm most proud of kind of seeing.
I think probably we might have to call it a day there, but it's been wonderful to talk with you all. I just wanted to share some really good news that the show, through huge popular demand, is going to be extended into the new year, which I'm really pleased about. So it's really nice to be able to keep the works within the building for a bit longer. So yeah. So that's really exciting. And then we've got the final lecture on the 9th of November, isn't it? So the fourth lecture will take place on the 9th of November. So please do attend that, which will be posted very soon. Thank you very much.
Thank you.
Thank you.